Homogeneous coordinates used for computer graphics of the point xy. xy1. A more generic answer, if you put xyh, I'll take that too, because I couldn't think of a way to tell you exactly what I wanted. xy what? Fine. xya. Okay, is translation a linear transformation? No. Since forever. So let's talk about linear transformations for a second. Remember, the definition of a linear transformation is that it has to preserve addition and scalar multiplication, right? So like t of u plus v has to equal t of u plus t of v, right? So let's talk about a translation that moves things 3 to the right, right? So if I have the point, let's pick 2 points, 1, 1 and 0, 4, right? So, hold on, this is a bad example. All right, let's have t of x be the function x, right? Okay, that's a linear transformation, okay, because it preserves the addition thing, right? So, but if I translate this, right, a translation would be t of x equals x minus 3. That's going to shift everything 3 to the right. Now, look at what happens if I do t of a plus b, right? That would be a plus b minus 3, right? Whereas t of a plus t of b is going to be a minus 3 plus b minus 3, which is a plus b minus 6, right? So they're not the same. When you do a translation, it's not a linear transformation. All right, a perspective projection maps a point in R3 to a plane or viewing plane. Either one is good. No, because a surface can be 3-dimensional. A homogeneous point, sure. A point in R2 is all right, I'll give it. Yeah, that was the answer. Sort of, this is how you do this in today's lesson. Okay, so we're talking about computer graphics today. So before we start the demo, I'm just going to like summarize the section. Okay, so computer graphics are made up of pixels, and coordinates of which pixels to show are stored in matrices. Okay, and you can manipulate an image, stretch, shrink, rotate, reflect it by performing matrix transformations on the coordinate matrix of the image. So you've got your whole image stored in a matrix, what pixels are supposed to light up, and then you can move those pixels around by matrix multiplication. Okay. So a translation, this is supposed to be an arrow, sorry. A translation that takes xy to x plus h comma y plus k, so it translates by h comma k, cannot be written as a 2x2 matrix transformation because it's not linear, right? Any linear transformation can be written as a matrix transformation, right? But this is not linear. We can't do it as a matrix transformation, a 2x2 matrix transformation. That's why we introduced the homogeneous coordinates. Okay, so instead of using xy, we use the homogeneous coordinates xy1. This means we're still working in a plane. It's just not the xy plane. It's 1 unit above the xy plane. And it allows us to be able to produce translations via 3x3 matrix multiplication. Okay. So if you want to translate xy1 to x plus h, y plus k, 1, you can use this matrix multiplication. Okay, so you take your point xy1, and you multiply by this matrix, okay? Exactly this matrix. So anytime you want to do a translation, use this matrix. You feel, it looks almost like the identity, except HK goes in the upper left 2 spots there. So, and then check when you multiply it. When you multiply the row 10h times the vector xy1, you have 1 times x plus 0 times y plus h times 1, which gives you x plus h. And then the next row gives you y plus k. And then the last row just gives you a 1. So this is sort of like, have this in your notes, or like memorize it or write it in your notes. That's how you make a 3x3 matrix that translates a point by h comma k. So you'll just pick what h and k are. That's for a point, yeah. What? They're not. That's why I had to. That's why we had to like do this weird thing where we work with the homogeneous coordinates, because we could not come up with a 2x2 matrix transformation that would move x, y to x plus h, y plus k. So this is like sort of a tricky little workaround that makes it work. Yeah, it's just like a placeholder to make it work. Yep. All right, and then anything other than a translation, like a rotation, a dilation, like a stretch, that's a stretch or a shrink. What else can you do? That's it, scale, rotate. And so those can always be done also by a 3x3, because now that we have to do 3x3 for translations, we're just going to work everything in 3x3. So we're not going back and forth. So the matrix for that looks like this, right? You do an L with zeros, a 1 in the corner, zeros above and to the left, right? And then the remainder of your matrix is A, okay? And A is the standard matrix for the linear transformation you're trying to do. So when you're creating 2D graphics, we always use homogeneous coordinates and 3x3 matrix transformations to manipulate or move the image. So this is also a thing you need to have in your notes. Okay. Yes. So therefore the matrix A has to be yes, A would be 2x2 because we're dealing with a 2-dimensional points on a screen. Yeah. Yeah. So by analogy, yeah, that's the next thing here. So when you're creating 2D graphics, you use homogeneous coordinates. That means 3, x, y, 1, right? And 3x3 matrix transformations to move the image. If you're dealing with points in R3, like to create 3D graphics, you use homogeneous coordinates, x, y, z, 1, right? And a 4x4 matrix transformation to manipulate the image. Sure. Yeah, I can print one for you. Yeah. Yeah. Okay. I'll do both. I'll post it to Moodle and I'll bring you one on Friday. Okay. And then the last thing from this section is perspective projections. Okay, so I thought that this was the trickiest thing for me to understand. I'm gonna erase this for a second. Okay. So perspective projections, like imagine, you know, when they do like really cool computer things that are a model of like a tumor or something, and like they can move it all around and like manipulate it on a 2D screen, but it looks 3D. Okay, so that's what they're talking about with a perspective projection. So here's how they do it. This is my computer screen. I'm back here, and between me and the computer screen is some 3D image, right? Like a tumor or a molecule, right? Some 3D image. So I draw a line from me through a point on my 3D image. So I pick one point on my 3D object, and I draw a point from me through that point and hits the screen, right? That is the perspective projection of a point in 3D into 2D. That's how they make these really cool 3D images on a 2D screen. So this is how it works, right? You map a point from R3, some point in R3, which is a point on your 3D object, into R2, and we go X, Y, Z to X star, Y star, 0. X star and Y star are the place where your line of sight hits the computer screen. Yeah. Yep. So you land in the XY plane, right? So it sort of takes things that are 3D and like pushes it all down into the XY plane. Okay, so we do this by creating a line, I just said that, through the eye of the viewer, which is on the z-axis at 0, 0, d. And the point where this line hits the xy plane, we call x star, y star, 0. So similar triangles are used to determine x star and y star, and the actual derivation was in your text, and you can read it. I'm not going to go through it. We're just going to be able to use it in the end, okay? But it's just similar triangles, some basic geometry. So the matrix transformation used to find the projection of any point that has homogeneous coordinates x, y, z, 1. So again, we're dealing with the homogeneous coordinates. Okay, so this projection, this matrix transformation, came from the similar triangles derivation thing, right? And it just turns out that this is what works. So for any point x, y, z, 1, you multiply by this matrix. I don't know why that's there. D is the viewer's distance away from the computer screen. So that is usually given in the problem. They'll say like the viewer is located at the point 0, 0, 10. The 3D model is between you and the computer screen. Doesn't matter where, right? Yeah. I mean, it does matter where. It's at each point of it is at some location x, y, z, 1. Right, but its location in relation to you is given by the points x, y, z, right? So this is your matrix. It's just, you'll just have to memorize it, right? You've got 1, 0, 0, 0, 0, 1, 0, 0, 3 zeros, and then negative 1 over d. D is your distance from the computer screen, and then 0, 0, 0, 1. Multiply by your homogeneous coordinates for each point on your 3D object, and you get this result that you are supposed to multiply by. So this is your result, right? This is the result when you do that multiplication. But I want the last coordinate to be 1, right? So that I have x star, y star, 0. And then I want that last one to be 1 because of our homogeneous coordinates. It's always supposed to be 1. So you just scale the whole vector by 1 over 1 minus z over d. So you just scale the whole thing by the vector, scale the whole vector by the entry in the 4th row. And we'll do one together. It'll be clearer. Okay, so now we'll do some examples. So I have a data matrix. This is a really simple, it's 3 points. I've got a triangle. So I have 0, 1 right here, 0, 0, and 1, 0. So this is a triangle. And I've stored it in a data matrix. So I'm not going to do anything with matrices or anything yet. I'm just going to draw what happens to this image of the data if I do 3 transformations, right? First, I'm going to scale the x coordinate by 2. Then I'm going to rotate about the origin 90 degrees. And lastly, I'm going to translate by the point 3,1. All right, so yeah, do it in the order that they say. Yeah. Oh, no, it's just the order that they say. Yeah, it doesn't have to be scale, rotate, translate. Yeah. Okay, so I underlined each one in a different color because I'm gonna draw each result. So I'll do green first. So I'm going to scale all my x coordinates by 2. So where does 0, 0 go to if you scale its x coordinate by 2? 0, 0. You multiply 0 by 2, you still get 0. How about 1, 0? Where does that land? 2, 0, just doubling the y coordinate. 0, 1, that goes to 0, 1. Okay, so I've got this new triangle here. All right, and then I'm supposed to rotate the result 90 degrees about the origin. So 2, 0, where does that go if I rotate it 90 degrees in the standard direction? 0, 2. Yep, it goes, rotates 90 degrees, lands up here. Okay. And then 0, 0, where does that land? 0, 0. And 0, 1, where does that go if you rotate it 90 degrees? Negative 1, 0. Good. Okay, so this is my new triangle. And then the last thing I do is translate that whole triangle that I just created by 3, 1, which means right 3, up 1. So each point, move it right 3 and up 1. So negative 1, 0 lands at 2, 1. And 0, 0 lands at 3, 1. And 0, 2 lands at 3, 3. So this is my final location of my graphic after I have manipulated it 3 different ways. Okay, so part B is to try to write, use matrix multiplication, 3 by 3 matrix multiplication, to find the image of the data under these 3 transformations. Okay, so how could I program a computer to figure out where these things land? Right? So I start with my data matrix, 0, 1. And I'm going to use homogeneous coordinates, right? So this is going to be 0, 1, 1, right? Homogeneous coordinates add a 1. Yep. And then 0, 0 is my next point, and I add a 1 for the homogeneous coordinates. And then my next point is 1, 0, add a 1 to make homogeneous coordinates. So I'm just going to label what this is. This is my data matrix. Okay. And then this is the weird part about this, is because matrix multiplication is not commutative, right? The first thing that's going to get done to this, I have to put in a matrix right here, right next to it, right? So what's the first thing that I do to my data matrix? Scale it, yeah. So this is going to be my scaling matrix. And then after scaling comes my rotate matrix. And then after rotate comes my translate matrix. So you got to go right to left, yeah. Yeah, it's a weird thing because of the fact that you can't change the order, right? You do, yeah. It's going to land in a different spot. Well, if you once you have it written out, you can multiply right to left. You just can't change the order of what I've written here. Then you can do the multiplication left to right. Yeah. Yeah. So the idea is, the goal is, if you want always to have these 3 things happen to whatever data you have, like if you're writing a whole program and this is what you want to do to all your points, you're going to multiply all these 3 together to get one 3 by 3 matrix that you can multiply your data matrix by to see where your data lands. So you're multiplying by the data matrix has to be last, right? You need to be able to multiply everything else together to get a transformation matrix that can then be multiplied by the data matrix. So that's sort of why left to right, because the data matrix multiplication has to be last, or right to left. So this has to be last. So then you have to do the order, scaling, rotate, translate. I know it's a little weird. Well, why can't we just write it, start on the left-hand side? I just told you why. Because you have to multiply by the data matrix last, right? Because we want to be able to combine these 3 matrices via multiplication to get one 3 by 3 matrix that you can multiply by your data matrix. Okay, so if you remember how to, so this one's linear, this one's linear, right? And the translate one is not linear, so this one is like a little different than the other 2, the way you set up the matrix. Okay. So when it's linear, you just put in this L. You just put in like 0, 0, 1, 0, 0, and then what goes in the remaining 2 by 2 spot is the standard matrix for the transformation that scales by 2. So let's just figure out what that is. The scaling by 2, scale x by 2. So in order to find the standard matrix, I have to know where 1, 0 goes and where 0, 1 goes, right? You all just did this on your quiz. Okay, so where does 1, 0 go if you scale x by 2? 2, 0. And where does 0, 1 go? 0, 1. These are the columns of your standard matrix, right? So I'm going to have 2, 0, 0, 1. That's my standard matrix for scaling x by 2. All right, and then if I want to do the standard matrix for rotate 90 degrees about the origin, same thing. I have to know where does 1, 0 go? If you rotate 90 degrees, 0, 1, you can just draw a little picture, right? 1, 0 will land there at 0, 1. And then 0, 1, where does that go? 0, 1 goes to negative 1, 0. Yeah, rotating in the same direction, negative 1, 0. Those are the columns of your standard matrix that will rotate 90 degrees about the origin. So I do my L, 0, 0, 1, 0, 0. And then in the remaining 2 by 2, I put these 2 points as my columns for the standard matrix. So I've got 0, 1, and negative 1, 0. And then my translate one was a little bit different, remember? So the translating matrix, it's almost like the identity. You've got 1, 0, 0, 0, 1, 0, 1 on the diagonal, and then H and K go there, right? And what did I translate by? 3, 1. So 3 is H and K is 1. That was how I translated. I was translate by 3, 1. So now we just multiply those 3 together, the 3 green matrices together, and I get one matrix that will tell me where my data goes. So yeah, let's have the calculator do that for sure. I think I actually just have the answer. Okay, so when I multiply the 3 green matrices together, which I think some of you are working on, but I know the answer, right? You get 0, 2, 0, negative 1, 0, 0, 3, 1, 1. This is all 3. This is the product of the 3 transformation matrices. Okay, so let's see what happens when I multiply that times my original data matrix. So 0, 1, 1, 0, 0, 1, 1, 0, 1. That's just my data matrix with homogeneous coordinates. So that's what I'd like to multiply together, and I want to verify. I already know where these points are going to go because we did it visually at the start. I want to make sure that this actually puts them there, this whole matrix manipulation thing. So this one I'll actually do in my calculator because I don't want you to just take my word that it does it. Okay, so matrix A, I need a 3 by 3, 0, negative 1, 3, 2, 0, 1, and 0, 0, 1. Okay, I'm going to edit matrix B and put in my 3 by 3 data matrix, 0, 0, 1. So now I want to do matrix A times matrix B. Whoa. Matrix B. There we go. All right, so my result is 2, 1, 1, 3, 1, 1, 3, 3, 1. Those are the points of my final triangle. 2, 1, 3, 1, and 3, 3. Right? 2, 1, 3, 1, and 3, 3. That's where my points landed. We can go back and check. 3, 3, 3, 1, and 2, 1. Yeah, the order matters because each point has to land in somewhere. Yeah. Yeah. You got the right points? Yeah. Good. So, like I said, there's just sort of a lot to remember and how to set these things up, but it's not super conceptually complicated. You just have to remember how to do it. Okay. Okay, so we got one more piece. We got to do an example of a perspective projection. Okay. Okay, so we're going to again start with a triangle just because it's a really simple image. It's 3D. It's a three-dimensional object because it's got points in R3. Okay. So I want to find the image of S under the perspective projection, where my center of projection, that's the eye of the viewer, is at 0, 0, 10. So this is an important transformation for 3D computer graphics, allows a person to view and manipulate 3D objects on a 2D screen. Okay, so I got to set up my perspective projection matrix. So that was 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, negative 1 over D, and 0, 0, 0, 1, right? And in this case, what's D? 10, right? D comes from the location of the viewer. Okay. So instead of negative 1 over D, I'm going to put in a negative 0.1. All right, so now that I have my matrix, I'm just going to multiply by my data matrix. Okay, so this is my projection matrix. This is going to be my data matrix. And I have to use homogeneous coordinates again. So my points are 7, 3, negative 5, add a 1 for the homogeneous coordinates, 12, 8, 2, 1, and 1, 2, 1 with the extra 1. So I'm going to multiply these together. And my result is going to be close to the answer, but not quite. Okay, so when I multiply these, I get 7 over 1.5, 3 over 1.5, 0 over 1.5. Oops, no, sorry. Sorry. These are wrong. The results are 7, 3, 0, 1.5, 12, 8, 0, 8, and 1, 2, 0.9. Okay. So the problem with this, we're almost there, but the problem here is that my bottom row is supposed to have no meaningful information in it. These are supposed to be just ones that like are making the arithmetic work. So what I do is each column I scale by dividing by the entry in that fourth spot, right? Because to make that 1.5 a 1, I could just divide it by 1.5. So this column, divide each entry by 1.5. This column, divide each entry by 8. This column, divide each entry by 0.9. They're not equal, right? I can't write equals the next thing, but that's where the projection lands. Yeah. Is that 0.8? Okay, I'll believe you. Okay. Oh yeah, it's definitely 0.8. Thank you. Okay, so I'm going to put an arrow here, right? When I scale the columns by different numbers, the matrices are no longer equal. I can't say they're equal. I'm just getting the final result of the perspective projection. So I put an arrow. So I scale, and my final result is 7 over 1.5, 3 over 1.5, 0 over 1.5, 1. And that comes out to 14 thirds, 2, 0, 1, 15, 10, 0, 1. If I divide every entry in this row by 0.8, this column by 0.8. And then the third column, divide every entry by 0.9, and you get 10 ninths, 20 ninths, 0, 1. So these are the coordinates of my three-dimensional points. This is where they land on a two-dimensional screen. Each column from the previous one, I divided every entry in it by the bottom entry. So 7 over 1.5, it just simplifies to 4 thirds. 14 thirds. Because the bottom is supposed to be meaningless. It's supposed to be just ones, placeholders. 0.9. Oh, yeah, they're divisions, yeah. Sorry, yeah. Yeah, I should have put divide by 1.5, divide by 0.8, divide by 0.9. Yeah. No, because 1 divided by 0.9 is 10 over 9. Yeah. 2 divided by 0.9 is the same thing as 20 over 9. Yes. So ultimately what happened is I had three-dimensional points. I had the three-dimensional point 7, 3, -5. And when I did the perspective projection, it landed at 14 thirds, 2, right? So it had coordinates in 3 dimensions. And then when I just looked for between me and the screen, I looked at the point 7, 3, -5, and the place where it lands on the screen is 14 thirds, 2. Okay. And then I had 2 other points. I had the center of the screen, because I'm on the z-axis. Yeah, yeah. And then my last point was 1, 2, 1, and it went to 10 ninths, 20 ninths in the xy plane. So again, just to summarize the process, you do this crazy matrix, right? That's just zeros and ones with the -1 over d in one spot. Multiply by your data matrix with homogeneous coordinates. And you get this matrix that doesn't have any meaning yet because the bottom row is supposed to be meaningless ones. So you just scale each column by the last entry in that column. And that gives you the final result. All right, that was kind of a long demo today, but you've got plenty of work to do on your own also.